guess Aaron Liu did for a while at least, and he did well. So a good thing. So let's figure out how to share our screens here. Yeah, here we go. Does anybody have any questions about last day before we start up here? All right, hearing no questions then, I'll begin. Yeah, so I want to talk today about electrolyte freezing. Obviously, if a liquid electrolyte freezes in a lithium-ion cell, it's not going to be very valuable because the ions won't move and you'll get no current from the cell. So I just wanted to start by talking about the water-salt phase diagram. Okay, it's actually pretty interesting, and you may not have thought of this before. Okay, so what do we have here? On the horizontal axis, we have percent of sodium chloride, and on the vertical axis, we have temperature. So if you start with pure water, which would be at the left side, it's a liquid until you reach 0 degrees C, and then it's a solid called ice. Now imagine we start with some salt content in the liquid, say on this red line, all right? Then when we move down, what happens is we hit a line called the liquidus line. And at this point, a portion, not all, but a portion of the sample becomes ice. And the other portion of it becomes water with a higher concentration of salt in it. So for example, if you move down to this red dot here, you would have some of the material frozen pure water. And the other fraction of the sample would be a liquid with a higher salt concentration than you originally had. Now, I don't know if people appreciate this, but this means that sea ice that you find along the shore of the ocean is virtually pure water. Okay? So you should pick up a piece of sea ice and melt it and see what it tastes like. Be a pretty interesting experiment. But the point of this is this type of a phase diagram, it has a liquidus line, and then another line here is called the solidus line. So once you move down through the solidus line, everything becomes a solid. And in this case, you would have a mixture of ice and this phase over here called sodium chloride .2H2O, also solid. So this is the liquidus line, and this is the solidus line. So let's take a look at some electrolyte phase diagrams, okay? Okay, so this is a little bit complicated, and we'll talk about it carefully so that we can understand it. So what have we got here? In the top panel, we have the phase diagram for EC, DMC, LiPF6, where there's no electrolyte salt. But there's something being plotted, X, and X is the EC fraction, okay? So what we're doing as we move to the right is we're adding EC to the mixture. But there's no salt here. Y is equal to 0, so it's just EC DMC. So what happens is when you cool the liquid down around 4 degrees centigrade in 2 sets of experiments, work by Michael Bauer in black and work by Michael Ding in the dots, the electrolyte freezes. So the pure DMC is liquid above this line and solid below this line, okay? And then as you increase the EC content, you have a liquidous line where the freezing point gets depressed, just like in water with salt, the freezing point gets depressed. So this is called freezing point depression. And if you cool below this point that you see here, you end up with a mixture of solid DMC and a liquid with a higher EC content than you had before. All right, so this may confuse some of you or surprise some of you that adding EC, which has a melting point of around 36 degrees, to DMC lowers the liquidus, the point where, you know, it first freezes compared to DMC alone, okay? So that's quite common. You would also think about the same thing over here. You add sodium chloride, which has a melting point, I don't know, several hundred degrees C, to water, and it lowers the melting point. And then there's these two horizontal lines at the bottom. These are solidus lines. Where you move below this line, everything is a solid, okay? So what it means is if you have an EC DMC electrolyte with very low LiPF6 content, it will solidify below -10 degrees C. And then if you put 1 molar LiPF6 into the system, it starts to become more complicated. And what are marked here are a liquidus line and then 2 other lines. Below line 1, everything is a solid, okay? So if you have an electrolyte which has 25% 25% EC, 1 molar LiPF6, what you will find is if you cool it somewhere around -8 or -10 degrees C, a portion of the electrolyte will solidify, and you'll get DMC plus an electrolyte with a higher EC content. And if you keep cooling down to -30, everything will solidify. So it's important to have this information about the electrolyte that you use in cells in order to operate them in an intelligent way. And in our laboratory, it means that if you're doing experiments like impedance spectroscopy and you're interested in -10 degrees C, you better think carefully about whether your electrolyte is liquid or solid or partially solid at that temperature, depending on what your electrolyte composition is. Okay, so any questions about this? So this guy, Michael Ding, he works at the U.S. Army Research Laboratory in Maryland. And Kang Xu and Richard Zhao, these are big electrolyte experts. Michael Ding has measured lots of phase diagrams for different electrolyte systems. So this is the phase diagram for DMC and EC with no electrolyte salt in the open symbols. So you have the melting point of pure DMC over here, 4.9 degrees C. The melting point of pure EC over here, 36 degrees C. And the liquidus line showing what's called a eutectic, which means the lowest temperature where you get a pure liquid. The composition where that is called the eutectic point. These types of phase diagrams are determined with what's known as differential scanning calorimetry or differential thermal analysis. So what you do is you make a mixture, you cool it to low temperature, and then you heat it up at a constant rate and you measure the heat flow necessary to heat it at a constant rate. And what you see is a feature at around minus 0.7 degrees C, which is the solidus line. So a portion of the sample has melted here. And then as you continue heating, you see this continual amount of heat flow, which terminates in a sharp cliff. And the position of this sharp cliff gives you the liquidus point. So between the solidus curve and the liquidus curve, as you move up, you're continually melting more and more of the sample at a higher and higher rate. Where is this here? This is for EC 0.854. Okay, so that's over here, 0.854. So you hit the solidus at minus 7.6. You can see that. And then you move up, 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 up. And finally, you hit the liquidus around 27 degrees C or so here. Yeah, 27.8. So from these calorimetry experiments, you can determine what the phase diagrams look like. Any questions about this?
Jeff, one question. So if we stay at this mole fraction of 0.8, just for the sake of the argument, so if there is no salt in the entire electrolyte, which is, I think, the case on this slide, then there will be solid EC in liquid DMC, right? That's basically what this region is.
In this region where my mouse is, you'll have solid EC and a liquid whose composition is given by the position of this line. So as the temperature increases, the liquid phase gets more and more rich in EC. You keep putting more and more EC into the liquid phase as you move up. The liquid phase moves along this line. And because you're continually melting EC as you move up, that's why this calorimeter curve doesn't just have a flat baseline here. You're continually melting things. Yeah.
Okay, so just for clarification, not all the EC is solid in this region.
That's correct. Once you move up into this area here, the liquid phase in coexistence with solid EC has some liquid in it.
Cool. Okay.
Yeah, there's a horizontal line you draw here. Let me go back to the previous slide. This horizontal line is called a tie line, and it joins the two phases that coexist together at a particular temperature and composition. So you can figure out the composition of the liquid phase by going to this point and reading down. So this is like 25% NaCl in water at this point. Yeah.
Okay. Okay, cool.
Thanks for that question. Any other questions? Okay, hearing none, I'll continue.
What is, Jeff, what is the functionality of this SO3 methyl NPF6 salt on the left panel? This
thing? Yeah,
yes.
Well, I didn't talk about this. So this is tetraethyl methyl ammonium PF6. So this would be called a supporting electrolyte, where you want to have some ionic conductivity, but you don't want to have any lithium ions around. So it's just used to probe transporting electrolytes in the absence of lithium ions. Okay, so now let's take a look at melting points of some of these common solvents that we use in the battery business, and I've highlighted that in the red box. So EC is 36.4. PC, only differs by a methyl group, and look, the melting point is minus 48. Incredible. DMC 4.6, and then EMC, just an extra methylene group, and it goes down to minus 53. And diethyl carbonate is minus 74. So if you're trying to make a really low temperature electrolyte, you would not focus on EC and DMC, right? EC, DMC. The reason we pick EC and DMC for lithium ion cells in general is we're not so worried about low temperature behavior, especially if you're working with a partner who warms their packs. And you want DMC in there to give you the best conductivity because it has the lowest viscosity of all these things, which you can see here. And you want EC because it is the best at passivating graphite of all these things. But if you're focused on a low temperature electrolyte, you would start putting some PC in for EC, and people do that, and put some DEC in for DMC, and people do that. And here's the phase diagram for PC DEC. It's liquid all the way down to -80, unless you're way over at the DEC side, so it's pretty crazy, right? You can make a really low temperature electrolyte if you want to. So any questions about this? All right, so that's the end of the melting point section. It was very brief. So now I want to talk about how you measure diffusion constants of lithium in electrolyte solutions. So there's a number of ways to do this. You can use NMR spectroscopy. I'm not going to talk about that method. I'm going to talk about this very simple method that many people use, but this particular paper by Lars Ole Valoen and Jan Reimers from Moly Energy is a really good one to take a look at. Very simple method. So what you do is you make a lithium-lithium cell, okay? And then you start a current flow from one side to the other. So you electroplate lithium onto the top electrode and you strip it from the bottom one. So these two lithium electrodes, they're exactly the same. So the open circuit voltage of this cell is 0. But when you run a current, the voltage of the cell is not 0 anymore because there's a concentration gradient in the electrolyte. And the voltage difference that you get is related to the concentration at the surface of electrode 1 and the concentration of the electrolyte at electrode 2 by the Nernst equation. It's given by this. Okay, so I'll remind you that KT over E is 25 millivolts. So 2 times 25 millivolts is like 50 millivolts. So if this ratio of C1 to C2 is 2.78, or the value of E, the log of E is 1. So these voltages you're going to measure are things the order of 50 millivolts or so. So to do this experiment, you have to measure things pretty accurately. And the voltage difference allows you to figure out what the difference between C1 and C2 is. And then you use the Fick's first law to get the diffusion constant, because the current density, J, the current divided by the electrode surface area, is related to the diffusion constant times the gradient in the concentration. So it's a very simple measurement and easy to do. So any questions about this? Okay. So in that paper, Reimers and Valoen measured data for the diffusion constant of lithium in PC, EC, DMC as a function of concentration and temperature, different temperatures shown here. So 270 degrees 3 Kelvin is 0 C, and they go up to 60 degrees C at 333. And you can see the diffusion constant increases dramatically with temperature and decreases dramatically with concentration. And it decreases with concentration because, as we mentioned before, the viscosity increases with concentration. Okay. So when you're operating a lithium ion cell at high current, we'll see in a moment that the concentration of the electrolyte is not the same everywhere. And you can also cause heating in the cell at high current. So it means the diffusion constant depends spatially where you are within the cell, from anode to cathode. And it also depends on regions of the cell that might get hotter than others, or regions of the battery pack that might get hotter than the other. Okay, any questions about this?
Yes, Jeff, why is the units of the diffusion constant centimeters squared per centimeter? Is there a different measurement? Why is that not centimeters squared per second?
Well, that's what happens when you proofread an article and you miss a typo. So that should be obviously centimeters squared per second. So it's not me that missed the typo here. It was Valoin and Reimers, right? Missed the typo in their figure caption.
Jeff, the 10% PC in this electrolyte, will it cause issues in SEI? Because it's PC is, the 10% PC, because PC is known to be harmful on the graphite anode side.
I think you can easily add 10% PC in the presence of 2% VC, and it won't cause any trouble at all.
Okay, I see.
Yeah.
Thank you.
So, and that will really improve your low temperature, lower the low temperature freezing point by adding that 10% PC. Okay, so now we need to talk about something called electrolyte depletion. And we're going to follow the treatment in McKinnon's chapter 7, which I've scanned and copied and emailed to you. And in that chapter, he uses a fairly cumbersome notation, and you have to spend a bit of time to figure out, okay, what's going on. And I haven't, jived up exactly with the notation in his thesis. What are we talking about here? So we're talking about a situation where you have two electrodes. It could be the positive and the negative of a lithium-ion cell, separated by some distance, and in between you have an electrolyte. And then when you pass a current, in order for the lithium ions to move from one electrode to the other, they have to feel a concentration gradient. Diffusion doesn't take place unless you have a region of high concentration and a region of low concentration. Things move from high concentration to low concentration. And then in addition, you can have electric field assisted motion because the carriers are charged. Okay. But anyway, the point is that if you assume the diffusion constant of the lithium is D, and assume it's independent of the concentration, then when you initiate a current flow between the electrodes and assume that one of them is at 0 and the other one is at a distance D, you can show that in this steady state, when the current is established and flowing between these electrodes, that current density is given by where the current is in, the current density is amps per meter squared. It's given by Faraday's number times the diffusion constant, which in this case would be, well, I guess you could use amps per centimeter squared, and then the diffusion constant would be centimeters squared per second, times 1 plus the charge of the positive ion over the magnitude of the charge of the negative ion. So for us, for LiPF6, this fractional term is 1 times the gradient of the concentration. So in a plane parallel geometry, the concentration gradient varies, the concentration varies linearly with position. So this gradient is very simple. It's just the concentration of lithium ions at the right electrode minus the concentration of the lithium ions at the left electrode. That's the change in concentration divided by the distance between them. So that's what the gradient is if you have a linearly varying function. So what this tells you is when you start increasing the current more and more, eventually you'll drive the concentration of the lithium ions to zero at one of the electrodes. At some point, the current will get so big. I mean, the current will be so big that in order to support that current, this gradient will become too large. And I'll show you what I mean in the next slide. So I just did some simple calculations here for a diffusion constant of 10 to the minus 6 centimeters squared per second. So pretty typical for a lithium ion electrolyte. And an initial concentration of 1 molar, again typical, and a spacing between the electrodes of 25 microns. So this would be, imagine from the front surface of one electrode across the separator, 25 micron separator, to the front surface of the next. And then you want to plot the molarity versus position between the electrodes when you're running different current densities. So if you're running 10 milliamps per centimeter squared, you can see you get a pretty small concentration gradient. And when you're running 20 milliamps per centimeter squared, it doubles. The concentration, the gradient doubles. And for our lithium ion cells, 10 milliamps per centimeter squared is about a 2C discharge typically. You know, we typically would have 5 milliamp hours per centimeter squared loading. So 10 milliamps per centimeter squared is 2C. And 20 milliamps per centimeter squared is 4C. So the point here is, you know, across a 25 micron gap, these kind of current densities can be easily supported. But the electrolyte has to conduct the ions to the backs of the electrodes as well. And that's just neglecting the fact that the electrodes aren't 100% porous, because the small porosity makes this far worse. But just say that each electrode is 70 microns thick. Well, then you've got to go 140 for the 2 electrodes and 25 for the separator being considered here. And then you can see at 20 milliamps per centimeter squared, you're virtually driving the electrolyte concentration to 0 at one of the electrodes. And obviously, if you drive it all the way down to 0, there won't be any ions left to conduct, and the polarization, the voltage, the overvoltage of the cell will become immense, and the discharge will stop. Okay. So this is why you have to think about electrolyte polarization, the fact that the concentration of the ions is not fixed between the 2 electrodes once currents are flowing. Okay. Now the other thing I want to mention is anywhere you look in the electrolyte, it's electrically neutral. So if you take a small patch of electrolyte and you ask how many lithium ions and how many PF6 ions are in this small bit of electrolyte, the answer is it's the same amount. So when you see the molarity go up to almost 2 molar on this side, it's 2 molar in lithium and 2 molar in PF6, both. Okay, both. The electrolyte always has to be electrically neutral everywhere. Okay, any questions about this?
So I guess that's why you see a lot in the literature, in the literature when people talk about rate capabilities. A lot of people tend to use very thin electrodes. I'm guessing they're just trying to overcome this practical problem, right?
That's exactly the case. When you want to build a high rate cell, you want high porosity electrodes and you want thin electrodes. That's exactly why. Okay, so then you can see the problem here. The problem is if you increase the current density more and just change the slope of this blue line a little bit to make it go through the 0, 0 point, that's the maximum current that you can flow before you get what's called electrolyte depletion. Electrolyte depletion means you drive the concentration of the electrolyte to 0 at some point. Okay. So what is the value of the current density when this occurs? Well, it's easy to work out. The limiting current is when the concentration is driven to 0 at some point. And that occurs when the concentration at the left-hand electrode equals 0, and the concentration at the right-hand electrode is twice the equilibrium concentration. So then you can work out the limiting current, and you get this expression. And this agrees with equation A9 in Atlum's paper that we're about to talk about. So on homework 5 that I emailed to you yesterday, there's one question that talks about this limiting current behavior that you're asked to estimate for a particular cell technology that we haven't talked about in class, but you'll learn about in the homework problem. Yeah, so Ahmed's question was right on. You know, this is all about the things you have to worry about to design a high-rate lithium-ion cell. And you know what, this limiting current doesn't take porosity and tortuosity of the electrodes into consideration. And we'll talk about how that's done, hopefully later on today if I get that far. Okay, any more questions about this before we move on to the next part? Okay, hearing none. Okay, well, this old paper from 1979 by Sven Atbaum, for me, this is a classic paper. And, you know, some of the people in our group are very familiar with this paper, but many of them aren't, and lots of others in the class are not either. But this was one of the first papers that talked about the impact of the diffusion of lithium within the electrode particles. You know, the lithium comes to the surface of the electrode particle and it has to diffuse into the middle. And that takes time. And what's the impact of this finite rate of solid-state diffusion on the performance of the cell? So that's what this paper is all about. And now my slide says this figure is really worth talking about. Spend the time. So I will. Okay. So let's talk about this. What do we have happening here? So what he's plotting along the horizontal axis is the position from the lithium metal negative electrode through the electrolyte. So the electrolyte has a thickness of D. And then imagine you come to a positive electrode particle where you describe the position in the particle from its surface to its center by this variable r. So the center of the particle, this center line, where he's labeled, r is 0, and at the surface of the particle, the value is equal to the radius of the particle, it's a sphere, or the thickness of the slab if it's a slab-like particle. Like this. This is a slab-like particle. So now let's talk about it. So here, the anode is lithium metal, and the vertical axis here is the concentration of lithium ions either in the electrolyte or within the solid. Okay? So you're discharging, and in a lithium metal cell, that means you're moving lithium ions through the electrolyte from the lithium metal to the intercalation cathode, and you're filling it up. So for lithium to move from the anode to the cathode, to move from the left to the right, there has to be a concentration gradient in the electrolyte. Otherwise, diffusion wouldn't take place. Okay, so that's where this concentration gradient comes from. And then, you know, whatever the concentration is in the electrolyte, it's in units of molar. Concentration of the lithium ions in the lithium TiS2 or whatever the electrode is, lithium cobalt oxide, whatever it is, it's you can express it in terms of moles per liter, and you can work out what the content of lithium in full lithium cobalt oxide is in moles per liter, and you'll find out it's not the same as in the liquid. You know, the lithium is very tightly packed in these intercalation materials. Okay, so you come along to the surface of the positive, and you know you're bringing lithium ions there at some rate, and they accumulate at the surface of the positive, and they have to diffuse into the middle. And that accumulation of lithium at the surface and then the start of diffusion into the middle creates a concentration gradient within the particle. Okay, and as the discharge continues, this line that you see moves up, and up, and up, and up, and eventually it reaches this point where the surface of the positive electrode material, so if it's titanium sulfide, you reach the limit, LiTiS2. You can't put any more lithium in, okay? You can't put any more lithium in, so the surface becomes full, but the interior is not yet full, okay, because of this, the shape of this curve. The surface is full, that means the voltage will drop below the cutoff point of your cell, of your charger. And there's all this capacity that you could have had, but you don't get. And then if you leave the cell open circuit, the concentration in the cell, in the material, will become uniform throughout the positive electrode at a value less than the limit, right? If you do the discharge at a slower rate, all the gradients will become smaller. All the gradients will become smaller than you see here. And when you reach the limit, you know, there will be very much less unfilled material, okay? And the reverse happens in the charge direction. It's exactly the reverse. So I really encourage you to read this Atlung paper. I think I sent it to you along with this batch of notes. I can't remember. But I definitely sent it to you with the homework 5. Okay, any questions about this?
Jeff, it is because for the cells discharge or charge, we do the CCCV, because the CV step is to eliminate this surface and the bulk concentration different.
Yeah, that's exactly right. So Wen-Tao's exactly right. What we do is we hold the voltage fixed, and that allows time for these concentration gradients to relax and for this unused region to fill up. So we don't do a CV step in discharge, but we do it in charge. So in charge, it means we try to empty the intercalation electrode completely in the CV step. If you really want to empty it completely, you would make the CCCV limiting current not C over 20, but something like C over 100 or something. It wouldn't add that much more time because those currents relax pretty fast towards 0. Okay, any other questions about this? I think this is a really nice figure, you know, to post on your bathroom wall and look at it every morning and say, yeah, you know, I really can appreciate what's going on in a real cell. And with modern first principles models of lithium-ion cells, you can calculate these things really easily. And I'll show you some results of that later on.
Hey, Jeff, what's the typical difference in magnitude between the diffusion, the electrolyte, versus diffusion, the bulk cathode?
Yeah, that's a great question. So good rule of thumb is diffusion constant in electrolyte is about 10 to the minus 6 centimeters squared per second. And within a solid particle, either graphite or lithium transition metal oxide, about 10 to the minus 9. So they're different by a factor of 1,000. And that's why we don't use electromaterial particles, you know, that are 50 microns in diameter or 100 microns in diameter. We keep them pretty small. And the electrolyte transport lengths, you know, from one side of the anode to the other side of the cathode nowadays is, you know, the order of 150 micrometers. So much, much bigger than the diameter of a particle, more like 10. And it's because of that diffusion constant difference. That's why that's the case.
Thanks.
All right, any other questions before we move on?
Quick question about the cathode. So if you were attempting to create the best high rate cell, would you attempt to optimize the gradient that you see there for the concentration as well, so that you would not need as long of a CV step?
Yeah, and there's two ways to do that. The first one is you increase the diffusion constant in the material, so that's a materials change. And the second one is you just make the particle smaller. So imagine that this center line was right here. Can you see my mouse?
Yep.
Yeah, so imagine the center line was right there. Well, then the amount of missing lithium when you get up to the top line, it's just a tiny little triangle. So for high rate cells, people will typically use small particle diameter positive electrodes and graphite. They'll pick smaller diameter ones. Make sense?
Yep, thank you.
Okay, any more questions? All right, so let's move on. Yeah, so in Atlung's paper, he shows you how you can treat the solid state diffusion within the electrode particles. And the treatment is at a level that we can follow in this class. I just need to switch over to my document camera to define a few things, all right? So let's try to do that. I think I have the wrong, you guys see me, right? Not the, how do I get the other camera? Got the camera plugged in, why isn't it changing over? Here we go. There we go. Great. So I think you can see the document camera, right? Is it true?
Currently, we still see the slideshow.
Really? Okay, let's see what happens now. How about
There we go.
Okay, great. So Atlung in his paper, he treats 3 different kind of particles. He treats particles that are flat, where he calls the center 0 and the surface R and minus R. So he called these plane particles, okay? And then he treats cylinders particles where the center is down the middle, obviously. And again, it's 0 at the center and R at the surface, so this is cylinder. And then finally, he treats spherical particles, where again, at the center, its coordinate is 0, and at the surface, it's R, okay? So this is a sphere. And these differ in that, for the case of the plane, the lithium diffusion is toward the center from both sides, and it's in one dimension. The lithium ions come from the surface, they diffuse to the center. There's no reason for them to diffuse at some strange angle, just by the symmetry of the situation. For a cylinder, though, they come in perpendicular to the surface everywhere. So this is two-dimensional diffusion. And this is one-dimensional. And the sphere, of course, the lithium ions come in perpendicular to the surface everywhere. I don't know how to draw it nicely. But the sphere is three-dimensional diffusion, okay? And what you'll see going into this lecture, when we get further along, that the rate capability, meaning the ability for lithium ions to diffuse from the surface to the middle, and to give you, to fill the most fraction of available sites, is best in the sphere case compared to the others. And that is one reason why electrode particles that you'll see in cells are generally spheres, not cylinders and planes. They're harder to make anyway, but it's good that a sphere is useful. Okay, so then let's go back to the PowerPoint. Where are we here, maybe? Yeah, here we are. Right. So x, this small x, is the variable that describes the position between the center at x equals 0 and the surface of those particles at x equals r. And he's saying that if you're starting a discharge with the cathode material empty, the concentration is 0 at t equals 0 for all positions within the particle. Okay, that's a boundary and initial condition. And then he says, for t greater than 0, at the surface, Fick's first law must hold. So the rate of, the concentration gradient of the lithium in the solid must equal the rate at which it's coming to the surface, so the current density in the electrolyte at the surface of the particle, divided by the diffusion constant. This is just d grad c equals j. That's diffusion equation. And then he also says for plane particles, for t greater than 0, at the center, the concentration gradient is 0 at the center. So I want to go back and explain why that's the case. I'll go to the document camera for a minute there. I think you can see the document camera now, right? Is it true?
Yes.
Thank you. So let's understand why the concentration gradient in the plane case is 0 at the center. So here we are with a plane, and we have 0 at the center and r at the surface. And we'll just plot the concentration in this direction. So we start, the concentration 0 everywhere, and we start putting lithium in at the surfaces, right? It'll go down, it's still 0 in the middle. But it has to show symmetry. It's a symmetric particle, so as you put more lithium in, you're always at 0 at a place where it's minimum concentration. So the derivative of concentration with respect to position is 0 because of this symmetry here. Okay? So that's what that other condition means. So go back to the PowerPoint. We're almost out of time. Whoops. Okay, is the PowerPoint showing up or not?
We're seeing your calendar.
That's funny. Let's get rid of the calendar then. Still seeing the calendar? Let's try this here. Electrolyte and diffusion. Should be this. How about that?
Yep.
Okay. So now we go to the next slide. Okay. So there's a lot of mathematics in this paper. And in the end, he comes down to this expression where he can tell you what the lithium content in the cathode is. So this capital X is not the position variable, it's the stoichiometry. So if you talk about LIX, TIS2, where that X varies from 0 to 1, this is what we're talking about. And this is a function of time and position in the particle. And there's an analytical expression for that, which looks kind of messy, that you can get from a book called Conduction and Heat in Solids by Carslaw and Jaeger. It's quite an interesting book. It treats heat flow in all kinds of geometries and in all kinds of boundary conditions. And the diffusion equation and the heat equation are exactly the same. So if you take the book by Carslaw and Jaeger and you look at it, you can find a situation, for example, diffusing heat from both sides of a planar solid, and you want to know what happens to the temperature versus time. So temperature is like the lithium content for us, and the heat flow is like the current for us. Okay, so this is just information that you probably will never care about. But, you know, when I was a graduate student and up until the middle 90s, you know, there was no Mathematica, there was no Maple, there was nothing like this at all. And really smart people worked out the solutions to these heat equation problems analytically and came up with these really interesting solutions, you know. And rather than reinvent the wheel, they published this book. It's about 3 inches thick. It has all these solutions, analytic solutions to the heat equation, and you can just go leaf through that thing until you find the solution that matches your problem. So it's pretty cool. Anyway, we've run out of time to talk about the meaning of these equations and what all the variables are, and then their impact. I'll do that next day. We'll probably spend 20 minutes next day finishing off this part, and then we'll have to move on to a new topic. I think the next topic I'll do is safety in lithium-ion cells from a sort of fundamental approach. So I'll email you those notes over the weekend sometime so that we can start on that at the second half of Monday. All right, so I'm going to stop here, and if there's any questions, it's a good time to ask them.
Hi, Jeff. I had a question based on like the diagrams you drew on the document camera. So when we are talking about the cylinders, why we are not considering a diffusion from the top and bottom side?
Oh, yeah, I understand. That's a good question. Yeah, we're assuming the cylinders are infinitely long.
But if we could make small size cylinder particles, in that case, like the sphere has lowest surface area to volume ratio. So if we could make like small size cylinder particles, do you think they could have better diffusion than sphere particles?
It's possible. It's possible. And actually, you can make small cylinder particles for the negative electrode side. If you use graphitized carbon fiber and then break it up into, you get small cylinder things. They look like paint cans or soup cans, you know. the reason they're not used is because you have to go through this fiber approach. And actually, you did a homework problem, right, where there were carbon fibers considered. I forget which homework it was, maybe homework 2. And you can make them, but they're too expensive to use. And in this particular treatment by Atlon, the infinite cylinder is solved exactly by Carcel and Jaeger, but the finite length cylinder I don't think is solved exactly in the book. So the solution's not available in an analytic form. Is that useful?
Yeah, definitely. Thank you.
Okay, I think Ron might have something to say.
Yeah, I have a question. So are the graphite domains considered cylinders because you can't intercalate from the basal plane?
Yeah, the graphite would be a very flat cylinder, right?
Okay.
More like
Thanks.
a pie plate or a dinner plate. Yeah.
Okay, thank you.
Okay. Any more questions? It sounds like we've reached a good point to end it for today. I'll see everyone on Monday.